Now we've seen that a negative value of delta G means that a reaction is spontaneous. But a spontaneous reaction cannot remain spontaneous forever. If it's spontaneous, it's going to be going forward. However, at some point it will reach a state of equilibrium. And so eventually it will have to reach a point where delta G is equal to 0, not having a negative value, but at equilibrium. This condition of the free energy of our change of our compounds is dependent upon the original value for delta G, but it also depends upon the temperature and also the reaction quotient. You see, a value for delta G at some given conditions, which is variable, it depends upon the concentrations of our reactants and products. It's affected by the ratio of the concentration of products and reactant Q. And also on the original spontaneity of the reaction at standard conditions. That is, the free energy change at standard conditions, i.e. at 25 degrees Celsius, and having 1 molar concentrations for all of our reactants and products, and 1 atmosphere pressures for all of our gaseous reactants and products. So again, there's some standard free energy change of a reaction, which gives us a good idea about how spontaneous it might be. But that spontaneity also depends upon how far the reaction is proceeded, how far Q is off from K, the ratio of products to reactants. These both affect the spontaneity of a reaction for a given moment. So, yes, a reaction will proceed until it's at equilibrium. It will proceed until Q is equal to K, until delta G is equal to 0. And so considering that we can take that original equation and replace delta G as 0 kilojoules per mole at equilibrium, and replace Q with K, the equilibrium constant at equilibrium. So we get this equation, which can be manipulated into delta G standard is equal to negative RT ln of K. And that also can give us K is equal to E to the negative delta G standard over RT. So this and that equation are key, as well as that original equation as well. These are all going to be used in referencing G versus K or Q. Now, please mind you that R, it's your gas constant. It's 8.31 kilopascal per moles Kelvin, but also it's also 0.0821 liters times atmospheres over moles Kelvin. However, R can also be 8.31 joules per Kelvin mole. Yes, if you're dealing with some equation which is dealing with energies, R is going to be that 8.31 joules per Kelvin mole, not 0.0821. Our temperature will be in Kelvin, and being that we are dealing with R, which is in joules per Kelvin mole, our delta G standard value must be in joules as well, joules per mole. Now, we'll use those equations later, but we can kind of surmise some ideas from these equations. Let's say that you have a negative delta G standard. So that is, we might normally say that the reaction is spontaneous, comparing the free energies of our reactants versus products. If that reaction is spontaneous, if we have a negative value for delta G standard, then that means that we will also have a positive ln of K value, and hence K will be greater than 1. We can see that having a spontaneous reaction, we are going to get more product than reactant at equilibrium. Now, we also can see that plugging in 0 for that delta G standard, so saying that at standard conditions where we have 1 atmosphere of pressure of both products and reactants, or 1 molar concentration of both products and reactants, and we're at 25 degrees Celsius, having a value of 0 there, plug in 0, means that ln of K will be equal to 0, which means that K will be equal to 1. And we also can say that R times T, the thermal energy within our system, is equal to 2.4 kilojoules per mole, if that's the case. If delta G standard is equal to that, 2.4 kilojoules per mole, then K is about equal to 1 as well, which is now important on the AP exam. And finally, if we have a positive value for delta G, then we'll have a negative ln of K, and then K is going to be less than 1. We can see that having a non-spontaneous reaction, we're going to have more reactants left over than products when equilibrium is reached. And so we can use this equation and these concepts to describe this very complex chart. You see, I'd like to draw out a case of the free energies of our compounds as the reaction proceeds, during reaction progression, where we're going from pure reactants to pure products on the right. Now, consider a case first in which we have a negative delta G, so standard. That is, the reaction is non-spontaneous. Actually, spontaneous. All right, so consider that you are making a graph of G as the reaction proceeds. You have a negative delta G standard. That is, there's a negative change. There's a loss in G as the reaction proceeds. So you start at a pretty high value for G and you end at a much lower value for that Gibbs free energy. There's a loss in that value, and so it kind of ends up so that we get this shape. Now, why do we have a shape like this, however, instead of a shape like going straight from one point to another? Why don't we get that? Well, we know that the system will tend towards the lowest energy. Just as a ball on a graph of potential energy or altitude is going on, we'll see that a ball will roll down a hill. Just like a ball will get to the minimal potential energy, reactions will proceed to the minimal free energy. We know that reactions don't tend to end up with pure reactants after the equilibrium is reached, or pure products after equilibrium is reached, but instead at equilibrium we end up having some mixture of both reactants and products. And you can see that here. You can see that the ball rolls down the hill from either direction to this point here, which has more products than reactants. It's to the right of the 50-50 mark. We can see that as the reaction proceeds, we do decrease in G. That reaction is going in the forward direction spontaneously if we had started with reactants. Or if we had started with just pure products, the reaction would go in the reverse direction spontaneously until we got back to that equilibrium state where that K is equal to Q. We can see that overall, if you have a negative delta G at equilibrium, you're going to get an equilibrium in which we have more products than reactants, where your equilibrium constant is greater than 1. And notably, the free energy of our system is going to be lower than either pure reactants or pure products. Overall, this reaction, as proceeding to equilibrium, it decreased the free energy of the entire system. And so that is spontaneous in either direction, at least to some extent. It spontaneously goes to the right, or it spontaneously goes to the left towards that equilibrium. Now, we could also say that as we went from reactants to products, Q was increasing. So we saw that as Q increased, we eventually had a point where Q was equal to K. So we could say that K is somewhere along that graph. All right, so consider another case in which your delta G standard is positive, it's greater than 0. Well, we know that that means that we'll have a non-spontaneous reaction. So it will proceed somewhat from pure reactants, or quite a lot from pure products. We're going to end up with a mixture of both reactants and products at equilibrium. Even though the reaction is non-spontaneous, it still occurs to some small extent from reactions. All right, so we can calculate, using those equations that were provided, we can see, here's the question, if you're given delta G standard, what's the Kp for that reaction? So, find the equilibrium constant. It's e to the negative delta G over RT. Be sure to plug in for your delta G as being joules per mole, not kilojoules per mole. And be sure to use 8.314 joules per Kelvin mole for R and 298 Kelvin. And so you get K is pretty close to 1. We can see that this delta G standard, which is 2.6, which is very close to 2.4 and to 0, has us with K being very close to 1. Yes. So this is a very small value for delta G. Delta G generally will range between negative 200 kilojoules per mole to positive 200 kilojoules per mole. If you have something about 0, K is about equal to 1. However, if you have a negative value, K is going to be much greater than 0, and if your delta G is very positive, K is going to be much less than 0. You can see that as you go further from 0 to positive kilojoules per mole, the reaction becomes less and less spontaneous. The K value becomes smaller and smaller. We can see that there is a strong relationship between delta G and K. The more positive the delta G, the less spontaneous and the smaller the value for K. All right, consider another question where we're told Kp and we need to find delta G standard. Use the following equation. Not complex, but what if I told you find the delta G, not standard, but delta G when you have the following pressures of things. All right, so for that reaction right there, so you need to go ahead and plug in for Q. Plug in for Q, that's the concentrations or pressures of products over reactants. And having the value for Q, you can plug in into everything else and find your delta G. You can see that that delta G does depend upon the ratio of products to reactants. And so the spontaneity of the reaction depends upon it as well. We can see again up in the graph that the spontaneity of any process depends upon the concentrations or Q. That's all. Thanks for watching, guys.